Okay, hi, welcome to class. We are here again today with our guest speaker, Dr. Bruce Douglas, who is joining us. He works for MITRE up in Virginia area, correct?
That's correct.
Close enough?
Yes, that's correct.
And reaching every, well, let me see if I can get this thing off the screen here. I apologize. I'm having some other challenges here. Do that. Okay. Okay, there we go. Now I've got control of my technology in the classroom. Okay, anyway, just to introduce Dr. Douglas, he's widely regarded as, like I told you guys in class, he is one of the leading experts in his field, and this is in the application of UML and SysML modeling. And this is specifically to the development of real-time and embedded systems. And he is actually one of the co-authors of UML and SysML standards. So if you've got any questions about the new SysML v2 that just has recently been released, which I do, of course, he is definitely the guy to ask for that. He has deep, broad expertise for over 40 years of experience designing safety critical real-time systems in a variety of hard real-time environments. He's designed and taught courses in Agile methods, requirements management, object orientation, which we just talked about last week, MBSE, real-time systems, engineering process improvement, which we touched a little bit on already, and safety critical systems development. He's the author of the Harmony process for embedded real-time development and over 6,000 book pages from a number of technical books, including the Agile Model-Based Systems Engineering Cookbook, published 2021, the Harmony AMBSE Desk Book, Agile Systems Engineering, Real-Time UML Workshop for Embedded Systems, and several others. He has consulted for many industries, including aerospace, defense, automotive, medical, transportation, industrial. And he also does detailed R&D engineering capability assessments and improvements worldwide. So that's quite impressive. He is formerly the chief evangelist and thought leader at IBM. He is currently senior principal Agile systems engineer with MITRE Corporation. He's done many presentations, models, papers, designs, and more, which can all be found on his website, which is up there on the screen. And I have his contact information if you need that. He's also in LinkedIn. So Dr. Douglas, welcome to our class. We thank you for taking your time today to come and talk to us about software architecting. I am a hardware girl, so this is totally a gap for me. So I'm going to be one of the students today too. So off to you.
Well, thank you. Thanks for inviting me. Today I'm going to talk about 6 different aspects of software architecture and what software architecture is. It's a very short kind of discussion. It's today, it's a big topic. And we're not going to get into great depth. Certainly try to ask questions. You can post questions in the chat. I'm on a second computer here, so I can see the chat questions. And I intend to have a kind of Q&A kind of at the end of this.
Okay.
So.
And I'll come off mute if there's any questions in the chat.
Okay. Susan already kind of gave you my bio. I am one of the authors of the UML standard and SysML standards. And SysML, by the way, is not out yet. It's not released. The plan is for an initial release November meeting this year, but it doesn't become an adopted standard until it goes through what's called a finalization process. SysML, that finalization process took 3 years. The initial release was in 2003. And the adopted standard became available in 2006. So it's going to be a couple of years from now before that standard appears, is what I expect. But it is coming. So if you have questions about it, I'm happy to answer the questions on it. So what is architecture? What do you mean by the term architecture? There are lots of people who have lots of different opinions. And I'll give you mine. To my mind, software architecture is a kind of design in which you make strategic decisions about optimization of system, structure, functionality, and behavior. So, and it's all about optimization. And so when you talk about these different aspects of architecture, we're really talking about how can I simultaneously optimize the system, structure, functionality, and behavior to meet my stakeholder objectives and needs in an optimal way. And what, by the way, do we mean by optimal? We'll talk a bit about that here. So again, architecture is a kind of design. So design in general is a set of decisions that you make about the structure, organization of system elements. Now collectively, they have to meet the requirements, the functional capabilities to deliver the behavior you expect, the functionality you expect to meet the operational needs of the system in this context. But above and beyond that, there are many architectures, many designs that could do that. How do we choose this architecture versus this other architecture? Well, we choose this one because we like it better. It's better in some sense. So there are always multiple architectures that could realize the same set of kind of functional requirements. So selecting one design over all the others is really a process of optimization. Now, when we talk about optimization, we don't necessarily mean optimization against just one criteria. There's a bunch of criteria, which I'll point out, some of them that are common. And you really pick a set of criteria, maybe worst case performance and resource usage and availability of working with available hardware and maintainability. And we maybe discard some of the other aspects, like how long does it take to develop? How many lines of code are required? You might want to optimize against size, code size. We take some criteria, and then we look at how important they are relative to each other. So we might want to say, resource usage, that's super, super important. Worst case performance, that's pretty important. If it uses a bit more memory, that's okay. It's important, but it's not as important. So we have this notion of a weighted set of design criteria, which are typically called measures of effectiveness, or MOEs. And we do essentially a trade study of different technical solutions to come up with what we consider to be the best design. So as I mentioned, there's a bunch of criteria you can use. Certainly, you should always optimize for simplicity. You don't want to have a Baroque, arcane architecture for no good reason. It should be as simple as possible, but no simpler than that. But there are other criteria as well, performance, and within performance, there's a lot of different aspects. Average performance, that might be important, or it might be absolute worst case. Average performance might be able to suffer a little bit, but we absolutely have to control the wing surfaces of our aircraft within certain tight time limits, or the plane will fall out of the sky. Those are typically called hard real-time systems, where we model the timeliness requirements as deadlines. We might want to have predictability of performance. As long as I can have an upper bound on performance, that might be good enough. We want to optimize for schedulability of performance. I want to schedule it using rate monotonic analysis or some priority-based schema like that. Resource usage, robustness of resources, thread safety, the ability to share resources across different threads without causing resource corruption or deadlock or race conditions. And then we have things like safety. Safety is freedom from harm. Reliability is a measure of the availability of services. Security is robustness in the presence of attack. Those are all related but distinct aspects of a system. Usability, portability, extensibility, ability to maintain it and add new features over time. Time to market, you might even want to be first in the marketplace, and that might be an overriding thing. You're willing to live with less functionality in order to get to the market first. Conformance to standards. You might want to build an avionics system which complies with DO 178, which is a civil avionics safety standard. And that has a whole set of rigorous criteria that your design must meet. in order to be certifiable for use in the airspace. And these are just some of the criteria. So you typically pick anywhere from 3 or 4 up to maybe a dozen of these, and those are your primary optimization criteria against which you will weigh and judge various designs. So when I think of design, I think of 3 basic levels of design. Beyond design, we've got what I call the analysis model. And this is where it is functionally correct, but it's not in any way optimized. It's functionally right, but it might be really slow and resource intensive and kind of cumbersome and arcane and complex, but it at least functionally meets the requirements. And then we take something which is demonstrably functionally correct, and we optimize it. So by demonstrably functionally correct, if you read any of my books, you know that I am all about modeling, right? And when I talk about modeling, I don't mean sketching something out on a napkin. I mean rigorously defining the structure, functionality, parametrics, and behavior of a system using formal or semi-formal approaches that are in fact computable. They're executable. So I can take my functional model and I can run it. I can say, well, what happens if I have these scenarios, these set of inputs with these values, they come in this order, sequence, and timing. What happens in that case? I expect this to happen. Is that what happened or not? So it's demonstrably functionally correct. It's not just something sketched out on a napkin. It is demonstrably correct. Many people optimize way too early, I think. So they get something which is really, really fast, but it does the wrong thing. And sometimes I've seen lots of people. I've been doing this sort of stuff for 40 odd years, and I've seen lots of people have really optimal systems that do the wrong thing. I don't think that's a win. So first and foremost, it has to do the right thing. Then we can talk about optimality. So you build this kind of functionality into the system, and then you can begin to think about optimizing it. When I talk about design, I think design takes place at 3 different levels of abstraction. The outermost level, the strategic level of design, we call architecture. And that's where you're making design decisions that optimize the entire system at once. So you get some sort of overall optimization. So you might say, for example, we want to have interoperability with a number of different systems, and we want to have a standard way to do our distribution architecture, which is distribution being one of the viewpoints of architecture, which we'll talk about. So we decide we're going to use the common object request architecture pattern to structure our system. So all of these subsystems, all of the various elements have to comply with that. So it's strategic in the sense that it applies overall and achieves some strategic level of optimization. That's architecture. Next step down in terms of more detail is what we call collaboration design. And that's where we think about a use case or user story, which consists of some set of design elements, typically residing somewhere in your architecture, that work together to realize some system function. If you're doing automotive, they talk about system functions. Some use case, which is a user-centric kind of capability of a system, or user story, which is typically a piece of a use case. And you optimize how that collaboration of these elements work together to achieve that particular more narrow goal. So that is typically an order of magnitude smaller in scope than system level optimization. So if you've got 50 use cases, you'll have kind of 50 different collaborations, although they may share common elements. There's overlap, that's fine. But they'll have like 50 collaborations. Each one of them is optimized maybe to a set of possibly different criteria. So that's collaboration level design. And finally, at the most tactical level, we've got what we call detailed design. And that's the design of individual functions, data structures, classes, blocks, those sorts of elements, individual pieces of detail inside our design. You might want to say that I want to optimize some individual element because as part of some important bandwidth throughput processing going on in my system. And so I want to optimize how this particular element works. We call that detailed design. So the design is some combination of all three of these levels of concerns. Now here, we're just going to be talking about architecture, but I want to cast architecture in the larger scope of how does it fit in with the other kinds of things that you do. So some guidelines that I teach in my practice for doing architecture. First of all, architect early. So if you're doing an agile method, an agile approach, so the Harmony ABMSE project process is agile, the agile model-based system engineering process. The agile real-time embedded software process, the Harmony ESW, also an agile process. There's this notion of what's called iteration zero, which is essentially the work you have to do before there's work to do, right? So you set up your progress, your program, your team, your development environment, capture initial kind of vision statements, your roadmaps, those sorts of high level kind of planning. One of the things you do is you create an initial architecture concept, which we call architecture zero. So that as you begin doing work, there are places, homes, if you will, for these smaller pieces of collaboration you'll create as you start working through the use cases and user stories or work items or however it is you're dividing up your system. They have a home to work in. And the architecture then evolves over time, but you start off early and with the intention that it will evolve over time as you get deeper into it. You evolve it often. So if you're doing an incremental development process, there's usually some technical work items to refactor your design, refactor your architecture in all of the sprints or iterations that you're going to do. The Agile approach, which is a depth-first approach, always kind of fundamentally requires refactoring. That you reorganize things, you'll add new pieces, you'll evolve it. Over time, it's just fundamental to the approach, as opposed to more traditional approaches, which are you do everything at one level of abstraction, and then you kind of ka-chunk goes forward one step, with a fundamental assumption that you can do so without making a mistake. Well, we know clearly based on, well, man-centuries of work that that's not true, right? You really can't do that. So Agile is a kind of response to that. So we'll do some depth-first approach to take some narrow piece of functionality all the way through, ultimately delivery of that, capability. And then we pop back up and then we add more stuff. So it's a depth-first approach. And as we do that, we pop back up, we say, okay, now I want to reorganize my architecture to take into account these new concerns which I'm now considering. And that is called refactoring. So we're going to evolve our architecture, and that evolution is typically called an architecture roadmap. Having said all that, we want to err on the side of simplicity. Don't add arcaneness just for the purpose of showing how clever you are. There's used to be in some of the C language magazines a column called C obfuscated, and somebody would write some really bizarre piece of C code, and people had to kind of guess, what does this mean? Well, I think that's just stupid. I mean, okay, so puzzle solving can be fun, sure. But you would never program like that. That would be stupid. That would be counterproductive. Don't be clever, be clear. Not that I have an opinion on that. Now, the way I practice architecture is a pattern-based approach. So I'll talk a little bit about design patterns, but a design pattern essentially is a proven solution to a certain kind of problem. And we'll talk about the properties that serve for patterns. But basically, a pattern is a reusable, proven solution where you can abstract away the specific problem details and take this general solution and apply it to novel circumstances, novel environments, novel problems. That's a design pattern. So inside our architecture, we'll have these 6 key viewpoints. A viewpoint in SysML is a subsection of a model focused around some particular concern. And in every viewpoint, there are alternative design patterns, different ways of solving the kinds of problems that show up in that viewpoint. So an architecture is really an integration of a set of patterns from all of these different viewpoints. And that's what we call the system architecture. So our good architectures tend to be pattern-based. Rather than invent everything de novo, we reuse good ideas that have worked in the past. The evolution of the architecture is done by application and creation of what we call technical work items. These are, typically when you have an iteration, you'll have a mission for an iteration, and it'll be doing new stuff. Those will be functional requirements and user stories and so on. There will be fixing defects you found in the stuff that you've already done, and other things you typically do in an iteration. You'll do some refactoring, and these are where these technical work items come in. You'll address some project risks by performing spikes, which is like a little experiment you do to learn information so you can resolve uncertainties and concerns. Right? And there, in the embedded systems, there's also an evolving nature of the platform you're going to target. Early platforms may be more virtual and simulated. Later platforms may use breadboards or hand-created wire wraps. Further along the project, you may have first-run factory boards. And so the hardware environment tends to evolve in kind of a standard way. So all of those things form the mission of an iteration. And one of the things in there are those technical work items, so you can refactor and pay down your technical debt. And as I mentioned, architecture, like all design, is all about optimization. This architecture choice is better than that one because there are reasons, right? There are essentially an infinite set of architectures that can't meet a set of functional requirements. And we want to find the best one that meets the overall set of needs that we have for our system and our stakeholders. Oh my God, write it down. It shouldn't be an oral tradition. And I'm also not a big fan of actually writing it down in like an architecture notebook, which is what some practitioners do. If you look at a book by Scott Ambler, and I love Scott, Scott's a great guy, but he's wrong here. Okay, he wrote a book called Agile Modeling. And basically in this book, he says, sketch out your idea on a napkin and then go somewhere else and do the real work. No, don't do that. That's dumb. Instead, what you should do is do your architecture in a more formal approach. And I think that you should generate the code from the architecture, from the design. Now, there are tools like Rhapsody that'll do this for you. You can create deployable code from the model, from the architecture, from the design. If you're using a tool where you have to write it by hand, fine. You can bring up Emacs or VI or Eclipse or whatever your coding tool is and bang out the code. That works fine, but it should ultimately be generated from your design. So they are different views of the same thing. It's not some sort of, something sort of kind of like that, but it is a formal statement of how these elements work together. And it should reflect exactly within the code. So the code is the model is the code, as far as I'm concerned. They should not be different work products. They're different views of the same thing, to my mind. And of course, keep the architecture current. If the code evolves away from the architectural description, then at some point it becomes useless and actively misleading. So it should be kept current. So normally you do what's called forward code generation. That is, you want to make a change to your design, whether it's refactoring or adding new functionality. You modify your design and work forward to come up with the code, the implementation for that. And again, whether you push a button in Rhapsody to generate that code, or you do that, you verify the model level, and then you say, okay, now I'm gonna bring up Emacs and bang out the code and do that. I don't care, right? But normally it's kind of a forward code generation approach, rather than let's just bang around the code, fix the code, and yeah, we'll get around to fixing the art design documentation later, because later never comes. I've seen far too many projects where that was the intent, but it's just failed and realized. All right. So let's look at a couple of questions here. A couple of firm systems I've been developing, they're complicated. Well, sure, architectures are complicated, designs are complicated. Yep. That's why marketing people don't do them. Okay, I'm not hitting too hard on marketing people. It requires some specialized expertise. So where do you start when you don't have a system architecture in place? So if it's a greenfield system, you don't have an architecture in place, you start with the architecture. Well, we start with the functionality, understand what it needs to do and what are the constraints. But then you build architecture kind of greenfield. If it's brownfield, that is, you already have a system exist, but you don't have an architectural description, then you should do architectural mining. Capture the as-is architecture, then determine what is the to-be architecture, where do you want to go, and the difference between those is the gap, and then you come up with an architectural roadmap that gets you from where you are to where you want to be. Two, how to implement this in your work to provide or sway those with authority. Well, there have been lots and lots of studies that it's just better, faster to do this. I mean, it's more effective. The reason why MBSE is all the rage now is because, well, it works. It's better than PowerPoint. It just works better. You end up with higher quality systems. I worked for consulting to a company in New Jersey doing avionics systems for the government. And so we did this study, and they found that there's 80% reduction in defects, delivered system defects, using a model-based approach versus not. In their case, right? Over what they were doing before. So typical work items to accumulate, they're part of the backlog, and every you have an iteration plan where you've got a set of iterations, and each iteration you've basically done some sort of quick allocation. These work items go to that iteration. So iteration 6 down the road, we expect to do these set of work items. Iteration 7 is these set, gets refined over time, and it gets finalized when you enter into that iteration. There's a culling of the work items when you start up a specific iteration and say, these are what's going to be allocated. Do we all agree on that? And then we work forward from that. But they get tossed into the work item list, the backlog, and they get prioritized. How important is it? How urgent is it? How critical is it? And then do we have the information to resolve the issue? And then so they get prioritized based on those criteria. And last comments on backlog. Yeah, so paying down technical debt those should be technical work items in the backlog. Because if you don't pay down technical debt, eventually the system will become unmaintainable, and you'll have to throw it away. That's just my experience. Okay. Let's talk a bit about design patterns. So design patterns is this classic book by the Gang of Four called Design Patterns. And they divide design patterns up into kind of 3 categories: creational, structural, and behavioral. I've written a couple of books on design patterns, one called, well, Real-Time Design Patterns, and this other one called Design Patterns for Embedded Systems in C. And in this case, I divide design patterns up into a bit more, with a bit more fidelity: creational, structural, behavioral, state behavioral. So I have a bunch of like state kind of idioms, small patterns for how to build up your state machines for different kinds of behavioral representational issues. Distribution, dependability deployments, resource concurrency. So those are how I divided design patterns up in that particular book. However you think about it, design patterns are generalized solutions to commonly recurring problems. And they're generalized by abstracting away the problem-specific detail. So I have a general solution that I can reapply in a different context. And there are 2 kinds of elements in the patterns. They are parameterized collaborations of objects, ultimately. So one of the roles that these elements play is called formal parameters. They're the place where you take the bits of your analysis model representation and they plug in into various places into your pattern. Those are the formal parameters of the pattern. And there are other roles, what I call the glue roles, that glue together and manage the behavior of the pattern as a whole. So there's these glue roles of elements provided by the pattern. And then there's the formal parameters where you take actual parameters, actual elements from your analysis model, stick it in to what we call instantiate or apply the pattern. So that's what this says here. Now patterns have, I think, 4 important aspects. One of these aspects is, what are the conditions under which this pattern is applicable? What are the conditions of applicability of the pattern? What has to be true, or what are the assumptions being made to make this pattern applicable? Second thing is, what aspects is it optimizing? And that's a really important one, because that's how we select, we want this pattern because this is an important criteria I'm trying to optimize it. You don't just optimize willy-nilly. I want it to be better. No, better how? We talked about all these different criteria. So you need to pick some specific criteria and optimize against those specific criteria. Because when you optimize, you're saying, these things are really important, and I'm willing to pay by being less efficient in some other way. There's always trade-offs. And you should do that with your eyes open. Be clear about what you're optimizing. Then there's the pattern itself. That's the solution. How does it work? What are the pieces? How do they connect up? How do they collaborate? And then finally, I think the most important part are the consequences. The pros and cons. The pros are, well, what problems does it solve? What are the good aspects? What are the outcomes that are considered good from the application of the pattern? There are also cons. There are costs involved using the pattern. There are things that you're de-optimizing. So when you select a pattern, you select it because it optimizes the things that are important to you at a cost that you're willing to pay. And there are always costs. It might be complexity, it might be memory usage, it might be performance. There's always a cost. So let's look at a quick example. So here we have an analysis model. This is a snapshot done in Rhapsody. This is for a train where we're doing speed control of a train. So we've got train speed. We've got speed here as a double. And we've got get speed, which is an operation that returns the value. Fine. Now, train speed associated with optical sensors. So there's a sensor on a wheel. It's a little light source. On the inside of the edge of the wheel, there are hash marks. And the wheel spins. We shine the light. We get a reflection back to a photoreceptor. And we can tell when the hash marks go by. Given a known size of the wheel, I can do the math and determine how fast the train is going. Okay, so that's how this optical sensor works. And it's going to use AD converter, it's going to use high pass band filters. These are parts of the optical sensor. And ultimately, determine basically speed from using this optical sensor. And you may have multiples of these if you want to have like multiple sources, that's fine. Now, you also have a couple of clients for train speed. One client is the speed controller. Speed controller is the motor system. Says I want to have this train go at 80 miles an hour. So I want to control against speed. If I slowing down, I put more power to the engine. Start speeding up, I maybe put less power, or maybe even apply brakes in some cases, so I can control the speed. I've also got some text views. In this case, you see star of those. There's a bunch of those. So in each car in the train, I can see the current speed of the train. So we've got these clients. So some optimization criteria. I want to be able to add new text views. I want to be able dynamically, when I assemble a particular train for the business purpose, might have 10 cars in this case, I might have 20 cars in some other case. I want to be able to add and subtract cars. And I want to be able to extend this design easily as necessary. So I can add and remove cars at runtime. Also, I also want to have an optimal use of my limited bus bandwidth. Maybe I'm using a multi-drop RS-232 link. Maybe I'm using a CAN bus. But I want to have an optimal bus usage. That means I only want to send data when it's important to send data, such as perhaps when the speed changes. Okay, so those are my optimization criteria. So I can look around and I can say, so what are the different patterns? And there's, it turns out to be a bunch of patterns that I could use. And this is one of them. This one is called the observer pattern. And there's a notation in UML for patterns. It's a dashed line with an oval here is called a collaboration. And remember, I said that a pattern is a parameterized collaboration. So here we've got the notion of an abstract subject. This is a subject of concern that clients care about. Now, the subject maintains basically a client list, which we call notification handles, which is an update address for all the clients that care. And there are services here so that observers can subscribe and unsubscribe. And what they're essentially going to do, we have an update operation, which is going to be invoked when we're going to update the data. I'm going to pass this address to the abstract subject when I subscribe, and I'll add a new notification handle with that address list. Then when it becomes appropriate to update my clients on whatever criteria I decide, new data is a common one. Then I basically walk my destination list and I let them all know. That's a way to do that. And then later on, if I want to have clients unsubscribe, then they can call to unsubscribe. So these are, if you will, the glue elements in my pattern. Then we have a subclass of abstract subject. Let's say subtype, so it inherits all the structure behavior of that and then specializes as it needs to. And this is a formal parameter of the pattern. So this is where I'm going to substitute one of my elements from my analysis model to instantiate the pattern. Similarly, abstract observer is also subclassed into concrete observer, and this is another formal parameter. And I decide, yeah, that's the one I want. Let's instantiate that. And then I come up with my design model, where I've now refactored my analysis model to enter in the design elements. So we see these elements coming from my pattern library package here. Notification handle, abstract subject, abstract observer. Train speed is a kind of abstract subject. And so it inherits this notify, subscribe, unsubscribe behaviors. There is an optical sensor, which still, so we can go get the data. And the text view and speed controllers are now subtypes of the abstract observer. Now notice in the original model, there is a relationship between train speed and text view and train speed and speed controller. That is replaced, so the system is refactored by this relationship here, because the observer can subscribe, and once it's subscribed, notification handle provides a kind of back channel back to the update operation provided to the text view and to the speed controller. So this is now an instantiated pattern based on that other pattern. So that's basically how patterns work. We come up with our analysis model, which is again functionally correct. We decide our optimization criteria. We find patterns that meet those criteria, and we instantiate it. So this is the basic workflow for how to apply design patterns. We build our analysis model, and by build it, I don't mean just, oh my God, I hope this works, but it's demonstrably correct. It should run, should execute. Then we identify my design criteria, as we talked about. We do use anywhere from at least 3 or 4 up to maybe a dozen criteria. We organize them in order of how critical they are to success. And if you want to know more, I give there's a talk on my website on how to do trade studies. So I give more detail on how to do that. Also on my YouTube channel, I talk about that as well. So we perform a trade study. So we look at alternative design solutions, patterns that could solve my problem. And then we pick one based on what seems to be the best fit for my particular problem. Then we instantiate that pattern to come up with our design model and refactor as necessary. And then I want to make sure that I did a good job. And there are 2 steps here. First of all, I want to verify. Remember, it used to work. It was demonstrably correct. I want to make sure I didn't break it. It should still work. So adding a pattern and doing some optimization and breaking it is no good. So first and foremost, make sure it still works. Secondly, I want to verify that my optimizations. I did this for a reason. Did I achieve my optimization goals? And if not, I apply different or perhaps additional patterns until I've achieved my required optimization. So that's how we apply design patterns. So that's background to talk about what architecture is and how we represent it and a bit about how we do it. Let's talk about the 6 dimensions of software architecture. Used to be 5. I added data recently because of the, mostly because of machine learning, frankly, because the notion of data as code. In a machine learning system, the data actually represents control information. So it actually is the program in air quotes, because it's the weighted set of inputs into your neural network. So for that reason, how we organize and treat the data is really, really important. So, and before it was kind of a second tier concern when I'm doing on one of the 5. So I've recently added it to the concerns for software architecture, largely because of the work that's going on in machine learning. Okay, so the 6 dimensions or aspects, fundamental aspects of software architecture are the subsystem and component viewpoint, the concurrency resource viewpoint, distribution, dependability, deployment, and the data, as we talked about. Let's talk about each one of these different aspects. The subsystem and component architecture viewpoint focuses on the identification and properties and characteristics of largest scale architectural pieces of the system, the subsystems, the components. Primary concerns are identification of those subsystems, allocation of responsibilities, services, and data into those subsystems, specification of the interfaces between those subsystems and the flows of information, and at a systems level, the other kinds of flows like fluid flows, energy flows, material flows, and so on, between the subsystems, as well as between the system as a unit and the elements in its environment. Construction of the system from its parts, a thing we call the composition architecture, and also variant management. Automotive, this is a crucial kind of concept. We build a number of different variants. We build this body with the diesel engine and this, infotainment package as one variant. This other one has the gasoline engine, 6-cylinder with the high tier infotainment system. That's a different variant. So we have to manage our variants. And there are ways that we can do that. So we have a number of different views that come up. System type context view, connected context view, system composition view, the system type architecture, interface architecture. All of those we typically represent with class diagrams in UML or block definition diagrams in SysML. The connected architecture and the connected context we do on internal block diagrams in SysML and things called structure diagrams in UML. They represent how things are connected in real time. So this is just an example of a class diagram showing how the elements are, and the connect in this case using ports as connection points. And this is how inside the vehicle they actually connect up in a running system. So what we call the connected architecture. The concurrency resource architecture really focuses on the concurrency units. They can be threads, they can be processes, they can be fibers, whatever your metaphor for representing concurrency units is. That's how we represent them, what they are, how we schedule them, and so on. It's all part of what we call concurrency resource architecture. And then also how we share resources across those threads. That has a huge impact on the system performance. This is a really strong determinant of the overall throughput, bandwidth, worst case performance, and average performance of your system. So the primary concerns are identification of the concurrency units, the thread processes and threads, and in UML and SysML, you do this by modeling what are called active classes. So not forks and joins and activity diagrams, but in fact, they're active classes which own the roots of threads and event queues to manage that. How do you split functionality across these concurrency units? And how do these different functions and data get shared across the concurrency unit? How do you share your resources? How are you going to schedule those concurrency units? Is it going to be something like a cyclic executive, multitasking preemption, round robin? What you going to do? How are you going to do it? How we access resources? We're going to use mutex semaphores. We're going to use queuing. There's a bunch of patterns for how we do that. How we access elements across concurrency boundaries so that we can avoid race conditions, unbounded blocking, which can affect your schedulability of the system to achieve its performance, avoid deadlocks, and so on. How you're managing timeliness concerns, processing deadlines and resource usage, and how do we avoid deadlock and race conditions. So here's a typical UML diagram for that. So in UML, the active class is shown with a heavy border, and some tools it's a double line border on the left and right edges of the classes. So here we see that there are 3 threads: measurement thread, visualization thread, and actuation thread. Now these could be structured classes, so they can have internal parts which execute in the context of those threads. We've got an interrupt handler, so it's kind of a 4th thread is an interrupt handler for processing incoming interrupts. We have a resource. This is a sensor, and it has queues for resource accesses, and these are the message queue is then managed via semaphores. We also have another resource here, which is a database. Database access is also managed through the use of resource semaphores, and we can characterize the concurrency metadata. Here, in this case, we've used a standard called the SPT profile, UML profile for schedulability, performance, and time. I'm one of the authors of that standard as well. There's others out there, like the more recent one is the MARTI profile, the modeling for analysis of real-time and embedded systems, another OMG standard. So you can model the concurrency relevant metadata, which can then drive the implementation concerns in your code. Distribution architecture viewpoint focuses on how do I distribute services and data across different processing nodes that are connected in some way. That could be networks, it could be multiple cores on a single processor, connected by shared memory or some other mechanism. Primary concerns is we want to specify the allocation of the services on these different distributed nodes, specification of communication links at various levels of abstraction. There's that 7-layer OSI protocol model. Top level, your application level services, like give me a radar track. Down below that, you'll have network services like create a session for requesting radar data. Below that, you might have data link. Here's a packet with some radar data in it. So we have these different levels, and so the different protocols exist at multiple layers of abstraction. And we want to specify that. We want to manage our qualities of service, such as availability and worst case performance delivery timelines. And we often do that with middleware, such as DDS, which is the data distribution service, or Corba, which is the common object request broker architecture. So here's an example using Corba for the distribution architecture, where we've got a furnace, a controller, a thermometer. And these all communicate remotely. They're all in different processing nodes in a building. So we have a furnace proxy, a controller proxy. These are created by a Corba IDL, interface description language. And then they leverage communication protocol stack to go to an object broker, which keeps track of where things are and then can manage the request forwarding for that. So this is just a simple example. We see these are Corba interface elements. In Rhapsody actually generate Corba IDL code for you from that. If you're doing it in a different tool, you may end up writing your own IDL, which is also certainly possible. The dependability architecture focuses on three concerns: is our ability to depend upon the functionality provided by system. The three primary concerns. The fourth one is privacy. Some people consider it a subtype of security, but I consider a fourth one privacy. Safety, freedom from harm. Reliability is a stochastic measure of the availability of services. And security is the resilience in the presence of attack. And of course, privacy is the protection of confidential information. So each one of these different sub areas of these pillars of dependability has a set of design patterns that you can use, that you'll use to construct an architecture that meets those concerns. If you look at my book, Real-Time Design Patterns, I have a whole bunch of different safety patterns around that. This is a fault tree analysis diagram using the UML profile, UML dependability profile, which I developed. This is in the Rhapsody tool. And here is an example pattern of what we call the homogeneous redundancy pattern, described in my real-time UML book, for which is used in many different safety critical systems, where we have multiple channels running in parallel. So if there's a fault identified in one of these, the safety monitor can switch control of the other channel. So we can manage safety in that way. And there's a bunch of different patterns, options you can select. Data architecture focuses on how you manage and use data. So the primary concerns are data storage and retrieval, data schema, how you represent the data schema, the data types, how they relate, their properties, their parts, the characteristics, and so on. How do you ensure the correctness of the data that you have in your system, and correct data when it's found to be incorrect? The availability of the information the data holds, data backup, recovery, and synchronization if you're doing distributed, reliable data systems, and the management of the metadata. That is the data about the data, such as range, unit, type, different kinds of qualities of service of the data, and so on. So how do you manage what we call the metadata as well? Here's just an example of a data schema for an aircraft system. We've got a flight property set with data around aircraft attitude, position, velocity, acceleration, jerk, which is the time derivative of acceleration. I didn't model snap, which is the time derivative of jerk, but sometimes in some systems you do. And the properties that they have, how the data relates to things. We see these metadata elements here, such as valid ranges and fidelity and accuracy and so on is required to achieve that. All of that should be specified in your data schema. So with respect to privacy, defined differences in demand for privacy across different groups. If you're shopping on Amazon, you might have privacy concern about who can see the fact that you're shopping for tutus or whatever it is you shop for. That's one level of privacy concern. Another one is a privacy concern about how many people must be able to see your credit card number. Right? And there's all different concerns have different levels of criticality. So yeah, so different groups have different concerns. And so you have to look at the data and the users and the consequences of misuse and what we call spillage to determine what patterns and approaches might be appropriate. So yeah. How do you do an architect for both high and low privacy? You typically model and design to the highest requirement. That's typically what I do. So if you over design it, it's more private than it needs to be, that's usually not a critical problem. Not private enough can be a critical problem. So yeah, that's typically what I do. But you could have it configurable as well. Finally, we've got the deployment architecture. The deployment architecture focuses on how we have different engineering disciplines collaborate in a system design. So I call the contributions of an engineering discipline, I call it an engineering facet. So we might have a software facet, an electronics facet, a mechanical facet, hydraulics facet, chemical facet, nuclear facet, and so on. So what are these engineering facets that contribute to the overall system design? And how do they coordinate, collaborate between these engineering disciplines? That's the primary concern. We spent a lot of time focusing on software to electronics. Because a lot of times that's where kind of the action is. And so we want to design that in a well-structured way so that the software engineers know how to access the features from electronics. Electronics engineers know what the expectations are for how those such features will be provided and what features will be provided. So all too often, it's left to one discipline or the other one and ends up with overall degradation of system performance because they just should have talked to each other. So we prefer a collaboration of the involved engineering disciplines. So here's what I do for that. So I use class diagrams and UML, block diagrams, and block definition diagrams, and this is, of course, would be an internal block diagram, and this is UML, so it'd be a structure diagram in UML. And so you see stereotypes here, which you really can't read. This is our software block, and this is not about the internals of the software design. There are other views for that. But if I think of the software in this subsystem, let's say, often it's done at the subsystem level, this represents all of the software. And these are the connection points between the software and the electronics. And these are defined by interfaces, which are empty, but they're shown around a boundary here. Defined by interfaces such as, that's interrupt mapped, this is memory mapped, that's port mapped. If it's memory mapped, this is the address. These are how I engage it. If you look at what the bits mean at the memory map, all the information is described in the interface that describes how the software talks to electronics. This is the electronics design that I've shown, in this case, just some high-level pieces. There's the thing related to timers, related to actuation control, related control of the hydraulics systems, and related to communications over the bus. And so the interfaces to support these different kind of characteristics. And then down here, we've got a mechanical block, where that's all the mechanical aspects, and their interfaces for electronics talking to mechanical pieces. Software doesn't talk directly to mechanical pieces, it talks to them via the electronics. So we don't see any connection from the software to mechanical parts. And here we have the hydraulics bits as well. This is what I do when I want to cast what I call the deployment architecture. What are the high-level pieces within the scope of this piece? In this case, it's a subsystem. Software contribution, software facet, electronics facet, mechanical facet, and hydraulics facet, and then a definition of the interfaces between. So in summary, that's a lot of stuff we talked about. But in summary, architecture is a kind of a design. It's what we call strategic design. Design is all about making technical decisions to optimally meet stakeholder needs. There are 6 key viewpoints we talked about, and where we have different focus of concern. Each one of these is characterized by a different set of design patterns. Patterns themselves are reusable technical solutions which have been generalized so I can apply them to novel technical circumstances. And architecture is then an integration of a set of strategic patterns, one or more patterns for each one of these key viewpoints. With that, I've written fairly extensively on these topics. And if you want to know more, I have a YouTube channel, and I also have my website. There's a bunch of papers and presentations and stuff there. So with that, that's what I have to say on the topic. I'd now like to open up for any questions you might have.
Thank you, Bruce. That was tremendous. I am a lot smarter now on the systems architecting side of software than I was before. We do have a couple of questions. I think you got to most of the ones that were in the chat, but we did have a couple that were posed outside of class. So one of the questions from Dan, he had asked, Agile software development seems to be geared to cloud and web computing. Does it work well in embedded systems?
If only somebody had a book about that. So if you look at the Agile literature, the vast majority of it is about 3 guys in a garage building a website. Absolutely, right? I mean, that's really where it focuses. And so I think that the ideas of Agile provide real value to engineering, but there is very little guidance on how do I do it if I'm building an aircraft engine, or if I'm building a CAT scanner, or a radiation treatment device, or an automobile. How does it work there? And so I've tried to fill that gap. And so the real-time agility book really focuses on embedded Agile software development. Now I view that there's 2 kind of different topics that are relate to each other, independent, but they relate to each other. One is Agile, and one is model-based development. And I think they're synergistic, and I always treat them together. You can do Agile without modeling, and you can do modeling without Agile. But I think they really work well together. And that's where I've kind of tend to focus my writings and my work.
Okay, good, thank you. Dan also had another question. He was asking, is making work fun for the younger employees part of the reason for moving to Agile software development?
Fun. Well, typically are in engineering, not because they couldn't do marketing. They're there because they like the technical stuff. They're nerds, right? I'm a nerd. My wife recently replaced the internal electronics of our big screen TV because it was fun. So we do things because we're nerds, right? So certainly I think there's that. And one of the things that as a nerd we don't like is stuff, doing things that just don't make sense. And so in Agile, there really is an emphasis on focusing where the work actually adds value. And I think that is inherently valuable, right? So yeah, I think to some degree that makes it more enjoyable because we're actually making a difference and we're not doing stuff just because it's a checkbox. Now, having said that, there are people who practice, air quotes, rigorous Agile, and they've got this Bible, and by God, come hell or high water, that's what they're going to do. No changes allowed, which kind of defeats the intent and purpose of doing Agile methods. The whole point of being Agile is to be resilient, robust, and adaptive to changing circumstances. Listen to truth on the ground and adapt to it. And so people who have this, the whole, we're going to follow this religious text because that's the way, Ken Beck said it should be done. That's just silly, right? Do what makes sense. And frankly, I think that engineers like that because they want to make a positive contribution.
All right, great. So I do want to go ahead and open it up to the rest of the class online. We have most of our class. We have a class of 10 students, and we have almost all of them online today with us in class today. So I'm really impressed with that. Thank you all.
Well, there is a question I haven't answered yet. So it's on the topic of executable models.
Okay.
SysML. What heuristics would you determine when you want to build a fully executable model? And the answer to that, as far as I'm concerned, is yes. So I guess when you care about the outcome, when you care about the correctness of the model. If you look at a model or any kind of statement in principle, going to epistemology, when you talk about falsifiable statements from epistemology, what that means is if you make a statement of truth, whether it's inductive or deductive, whether it's imperative or declarative, you're making a statement of truth. A falsifiable statement is a statement that if it's wrong, there's in principle ways you can demonstrate that it's wrong. That's what we mean by falsifiable statements from epistemology, right? Applying that to engineering, there are only so many ways you can tell if your design, your architecture is correct or not. One of them, and there are basically three, okay? One of them is you can look at it. And if you're doing kind of vague models that don't execute, that's the only thing you can do. You can look at it. Yeah, that seems kind of right, but that's the weakest possible form of verification. It's not like it's bad. I recommend you do that. In fact, in the Harmony process, we have a workflow for how to do effective inspections and reviews based on Michael Fagan's work. So that is valuable, but it by itself, it's insufficient. We don't trust Joe to write code for the nuclear power plant control without making a mistake. So we don't just look at Joe's code, we test Joe's code, right? So the second level of robustness here for verification is to test the model. Now that means that we want to take a set of test cases, that is inputs with particular values, sequence and timing, with a known and expected output or outcome. And we apply it to the work product and we see, do we get what we expect? That's true in code, that's also true with models. So it gives us a much more rigorous way to say, is my model correct? Does it actually make sense? Somebody early on said models are complex, designs are complex. Absolutely, that's why we need to do this. Because the chance of finding all the mistakes in a model just through inspection are for a big model of consequence, are essentially zero. The third level, as long as I'm rounding this out, is what we call formal methods. And that's where we represent our statements using a formal language like Z or predicate logic or temporal logic. And then we can do things like formal theorem proving. That has value. It turns out to be really hard to do. That does have value. In a project I worked at NASA JPL, we applied formal methods to maybe 2 or 3% of the problem because it's just that hard. But when you have some really critical part of the design, you might also do some formal methods. So my recommendation is use all three at various levels of application, but I tend to heavily emphasize testing because that gives you a big bang for the buck. So when should you apply it? When you care about whether or not it's right. Secondly, it says, so system is used to communicate. Okay, but not do something rigorous. There's this notion of PowerPoint engineering. It's not engineering. PowerPoint is not an engineering tool, it's a marketing tool. Now, again, I don't mean to beat on marketers. They get to live like the rest of us, fine, but it's not engineering. So I never use SysML Lite, as you call it, because I care about whether or not I'm right, because the systems I build are largely high reliability safety critical systems, systems like the advanced battle management system. You get it wrong, people die. Things like aircraft designs. I was one of the designers of that new aircraft carrier released by the Indian Navy. We care about those things because if you get it wrong, people die. So it's just, part of my experience is that the systems I build are high reliability, safety critical systems, and the consequences of failure are high. So if you're building a system where you're doing a website, with 3 guys in the garage, and it doesn't matter if it works because you just take it down, you fix it, patch it up, throw it back up there. Fine, your mileage may differ. Not every system is safety critical, but if you care about whether or not what you're saying, the statements you're saying with your design are true or not, you should be doing executable models. That's my view.
So it sounds an awful lot like it's tied to your risk posture programmatically.
Yeah, yes, I'd say that's true.
Yeah, because you can't afford to do everything. So at some point you have to figure out just how far down that rabbit hole you really want to go. But like you're saying, the safety critical items, I mean, I don't know that there's an answer on how far down you go if it's not the bottom.
Right. So that's just like fundamental. And you have to decide at what level. Well, you always have questions about with testing, one of the downsides of testing is you can't fully test everything.
Right.
Non-trivial system. There's essentially an infinite case of possible test cases, right? So you end up saying, what level of coverage do I need? What level of completeness do I need? And the DO 178 safety critical standard identifies several such levels. There's statement coverage, where every statement is executed once. That's already more than what most people do, but fine. There's decision coverage, where you basically test the true and false cases for every decision, as well as every line of code. And then there's MC-DC coverage, where you within a decision, you independently vary each predicate of that decision. That's called MC-DC coverage, which is much, much harder as it happens. So you can decide at what level of criticality your system is and how important correctness is for that to support that level of criticality. But you can't get to the basic level of coverage if all you look at it.
Okay. Are there any other questions? I see Dan had one question about, did you ever meet Rich Stotts at MITRE?
No, I've never met him.
Well, Dan, you may
People working.
have to make an introduction.
Yeah, there are 5,000 people working at MITRE. I don't know all of them.
Just a few. Well, we're about to the end of our class period, but I just want to thank you again so much for coming and presenting to us. And I will see about packaging up the recording and getting that out to you as well. But we will have this online. Just a reminder to the students, if you would, your feedback forms are part of your grade. Please include those when you have a chance. And anything else you have for us, Dr. Douglas, before we sign off?
Well, I hope this was useful and interesting. I do have my opinions. You probably figured that out somewhere after slide 1. But they're based on my experience of developing systems. And the kind of systems do, in fact, color my perspective. I tend to err on the side of making sure it's right. I don't know that that's a terrible perspective to have, but that does color my perspective over what somebody else might care about. With that caveat, I hope this was potentially useful for you.
Okay, well, thank you very much. Appreciate your time. I'll go ahead and stop recording.